Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element platinum. I have a sample of platinum right here in this file. You can see it's kind of a helically shaped wire. I put this on my scanner so that you could see it better. Here it is right here. If we magnify it, you can see the wire just a little bit better. It's a very shiny silvery metal. Here we see the beautiful periodic table produced by Theodore Gray. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to pick up. Check out his fantastic website, periodictable.com. Platinum is the 78th element in the periodic table. Its atomic number is 78 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. Platinum may have been known to the ancient Egyptians. For instance, a small box from the burial artifacts of Shepenupet II was found to be decorated with gold-platinum hieroglyphics. However, they may not have recognized platinum as a separate metal. Platinum was used by Native Americans near Esmeraldas, Ecuador, to produce gold-platinum alloy jewelry. But this platinum was probably not pure, having been extracted with other platinum group metals. This was almost 1,000 years later than the Egyptians' incidental use of platinum. Here you see a funerary mask. And here's another example of exquisite gold and platinum jewelry from the La Tolita culture further south in Ecuador. A year before his death, an Italian philosopher, medical doctor, and botanist, Julius Caesar Scaliger, described a metal found somewhere between Panama and Mexico, which no fire nor any Spanish artifice has yet been able to liquefy. Platinum has a pretty high melting point, as we'll see. I haven't been able to determine why he was familiar with Spanish work on the metal, as he worked primarily in Italy and France. Antonio de Ulloa and Jorge Juan y Santacilla observed Native Americans mining platinum in 1735. Ulloa took platinum nuggets home to Spain and began to systematically study its properties. However, he never went very far in his studies of the metal. In 1741, a British metallurgist, Charles Wood, gave samples of Colombian platinum he obtained in Jamaica to his brother-in-law, William Brownrigg, for further investigation. After a series of experiments, Brownrigg concluded in 1750 that it may be endowed with some peculiar qualities that may render it of singular use and importance to mankind. He recognized it as a new element and is credited with its discovery. Ulloa called the metal platina, which literally translates to little silver. This eventually became platinum. Platinum is part of a large group in the middle of the periodic table called the transition metals. This section of the periodic table is where we fill the d electron orbital of the respective atoms as we move left to right across the periodic table. Platinum is also a member of the platinum group of metals. Duh! That occurs in the middle of the periodic table. The 6 members of the group are ruthenium, rhodium, palladium, osmium, iridium, and, obviously, platinum. They all have similar chemical and physical properties and usually occur together in the same mineral deposits. Spirulite is one of the minerals where platinum is found. It forms these beautiful silvery crystals. It's mostly a platinum arsenide, but since the platinum group of elements is usually found together, there's usually a bit of other platinum group elements in there too. One of the places you find platinum ores is in Ontario, Canada, near the town of Sudbury. It was discovered here in 1888 alongside copper and nickel. Here you can find the Big Nickel Mine, which produces a rich variety of metals. When I was last there, quite a while ago, they gave a fascinating tour of the mine. Near the mine, on a beautiful lake, is a gem of a museum called Science North, with a unique snowflake-inspired architecture. I encourage you to visit this innovative and interactive science center if you're in their area. Normally, platinum ore isn't as pretty as the spirulite. Here you see platiniferous pyroxenite, a member of the igneous pyroxene family. In the chemical formula, the X and Y are replaced with other elements and, in our case, also have some platinum mixed in. This sample comes from South Africa. South Africa's Bushveld igneous complex, just to the north of Pretoria and Johannesburg, is the major source of platinum group metals and provides about 3/4 of the world's platinum. Platinum, the red stars appearing right now, is found on the borders of the geologic zones. Nickel, copper, and other platinum group metals are also found here. The world produces only about 189 metric tons, or 189,000 kilograms, of platinum annually. The vast majority of the world's platinum, about 74%, is mined in South Africa. Russia produces about 11% of the world's supply, and Zimbabwe about 8%. The remaining 7% is produced by Canada, the U.S., and others. The Big Nickel Mine only produces platinum as a byproduct. Not surprisingly, South Africa also produces the majority of the world's supply of the other platinum group metals, since they're usually found together. At least since 1990, the world production has been relatively flat between 150 and 200 metric tons per year. Platinum is pretty pricey stuff. Depending on purity and the quantity you buy, it'll currently, in 2024, run you about $800 per troy ounce, or about $29,700 per kilogram. Here is the historical price of platinum since 1970 in dollars per troy ounce. Looks like platinum would have been a good investment if you had bought it before 2000. It's more than doubled its value since then. Of course, double in 24 years is only a 3% annual increase. Note, I'm not giving any advice about buying metals as an investment. Platinum is a very beautiful silvery metal. This is a very small native crystal of platinum, only about 2 millimeters across. The element platinum is one of the rarer we've dealt with so far, coming in as the 45th most abundant element in the universe by mass, only 5 parts per billion. Almost twice as abundant in the Sun, it makes up 9 parts per billion of its mass and is the 38th most abundant element there. It's the 41st most abundant element in meteorites at 9.8 parts per 10 million. Very uncommon in the crust of the Earth, it's the 72nd most common element at 3.7 parts per 100 million. Gold is more rare by 10 times at 3.1 parts per billion, though platinum is more expensive. Go figure. Platinum is undetectable in the oceans of the Earth. And lastly, like most of the elements in the upper reaches of the periodic table, there's no platinum in us. This complicated version of the periodic table shows the evolution of the elements through the history of the universe. Here you see each element square with a tiny chart of its own, showing that element's growth over the age of the universe by various processes. Platinum is here. I understand this looks complicated, but let's look at just platinum a little closer. The horizontal axis of this square represents time, from the Big Bang to now. The vertical axis shows the proportion of platinum created by various processes. Less than 1/6 of platinum present today is believed to be produced by dying low-mass stars, the magenta area. Most of the rest is produced in supernovae, the yellow area. A very, very small portion, that green icing on the top, is produced in neutron star mergers. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same, 78 protons for platinum, but there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different weights. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 37 known isotopes of platinum. Of these 37, there are 5 stable, non-radioactive isotopes. These 5 stable isotopes are found in different proportions in nature, from almost 0.8% to almost 34%. The astute among you will probably notice that these 5 isotopes do not add up to 100% of the platinum in the universe, only 99.986%. Well, where's the missing 0.014% of naturally occurring platinum? There's actually one very long-lived radioactive isotope that makes up the rest, platinum-190. This isotope makes up the remaining 0.014%. More on this in the next slide. By the way, the word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place, since all these various forms of platinum occupy the same place in the periodic table. Of the radioactive isotopes of platinum, these are the longest lived, the ones with half-lives over 1 hour. More on half-life in the next slide. The longest lived platinum half-life is platinum-190, with a half-life of 483 billion years. That's over 35 times the age of the universe. With such a long half-life, you can see why platinum-190 still occurs in nature. It hasn't had time to decay away yet. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of, well, any isotope from the previous slide. I chose 1,024 atoms because it's a power of 2, and we'll be doing a lot of dividing by 2. If you wait one half-life, half of your isotope will decay, and you'll have 512 atoms left. If you wait one more half-life, half of that half decays, leaving you with 1/4 the original 1,024, or 256 atoms. Another half-life, half as many again, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, you'll have about 1/1000th of your original amount. By the way, notice there's one remaining atom after 10 half-lives. If you waited one more half-life, your remaining atom would have a 50-50 chance of decaying in that time. Platinum has the 3rd highest density of all the elements at 21.45 grams per cubic centimeter. As a reminder, water has a density of 1 gram per cubic centimeter. I've put up more densities for you here. You can see platinum is a little less dense than the densest element, osmium, a mere 1.14 grams per cubic centimeter higher. Here's a graph of the elements from highest density to lowest density. I have a set of blocks so you can feel density for yourself in my live talks. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, to magnesium. They also have plastic and wood blocks, but those are not technically elements. Again, platinum's density is 21.45 grams per cubic centimeter, the magenta circle. Its density is just slightly less than osmium. I'd love to have a cube of this stuff, but at its current cost, that cube would be almost $119,000. Any platinum refiners out there? I'm open to the donation of a 2¼ inch cube if you're so inclined to add to my collection. It would be really nice to have a cube at the high end of the density scale. That cube would weigh 4 kilograms or 8.8 pounds. Platinum has the 17th highest melting point of the elements, at a fairly high 1,768.3 degrees Celsius or 3,215 degrees Fahrenheit. Platinum boils at a high 3,825 degrees Celsius or 6,917 degrees Fahrenheit, giving it the 18th highest boiling point of all the elements. That's 2,057 degrees Celsius above its melting point. Platinum has the 19th largest liquid temperature range of all the elements. One of the subscribers to this channel, SillySad3198, thought it might be nice to see a graph of liquid temperature ranges from highest to lowest. So here it is. The widest liquid temperature range is of neptunium, 3,356 degrees Celsius, all the way down to neon, only 2.51 degrees Celsius. Platinum is the 18th widest liquid temperature range at 2,057 degrees Celsius. Notice all the noble gases, and hydrogen, have very small liquid temperature ranges. If we compare the size of the platinum atom to that of hydrogen, we'd see something like this. The platinum atom is about 3 1/3 times the size of hydrogen. Here's the electron structure. By the way, a picometer is a trillionth of a meter. Atoms are seriously small. Looking at all the elements' atom sizes, here we see them sorted from largest, cesium at the top left, to the smallest, helium at the bottom right. Platinum has the 34th largest size atom of the elements. Platinum is pretty soft stuff, coming in at 3.5 on Mohs scale of hardness. It's harder than gold, silver, and copper, but softer than iron and nickel. This is a chart of the element hardness from the hardest, boron, on the left, to the softest, cesium, on the right, obviously not including liquids or gases. Platinum is the 26th hardest element, between iron and arsenic. Platinum has the 21st lowest rate of thermal expansion of all the elements, only 8.9 parts per million per degree Celsius. This means that if you had a 1 meter long bar of platinum and you heated it by 1 degree Celsius, it would get longer by only 8.9 millionths of a meter, or about 1/5 the diameter of a human hair. A pretty low expansion rate. Here's the periodic table of the spectra. If you excite atoms, they give off specific colors of light. Platinum has a moderately complex set of emission lines across the spectrum. If I increase the contrast to remove the background, you can see these colors more plainly. These emission colors uniquely identify the element as platinum to scientists. No other element gives off this set of colors. Let's take a look at a few applications of platinum. What you see here are very pure vapor-deposited crystals of platinum. Platinum is used in many industries, but by far, most platinum, 61%, is used in the automotive industry. Then, as we see, about 10% is used in the chemical industry, about 8% used for jewelry, 7% for electronics, and the other 21% for various other purposes. Inside your catalytic converter is a honeycomb-like structure with platinum deposited on it. That's why catalytic converters have become a target for thieves. The platinum causes toxic unburned hydrocarbons in the exhaust to react and become less toxic but still problematic gases such as CO2. The converter can also reduce nitrogen oxides. In doing so, catalytic converters heat up tremendously, glowing red hot. It's called a catalytic converter because platinum is a catalyst, which is not consumed in the reaction. Copper spark plugs have an expected lifetime of 20,000 miles. Spark plugs with platinum-tipped electrodes can last as long as 100,000 miles. Platinum-tipped spark plugs are more expensive, at a price point of $5 to $15 per plug, depending on the model of your car. Platinum is used widely in the petroleum industry as a catalyst for many chemical reactions. Again, a catalyst speeds up reactions, but is not consumed in those reactions and remains unchanged. Fuel cells that turn hydrogen and oxygen into electricity use platinum as a catalyst in the process. This is a tiny version for educational purposes you can buy for around $20, but don't expect it to power anything more than an LED. I want to emphasize here that platinum is resistant to virtually all chemical reactions. To dissolve it, you must use one of the strongest acid solutions known, called aqua regia, a mixture of concentrated hydrochloric and nitric acid. Here, you see a 1-ounce bar of platinum slowly dissolving in heated aqua regia. Don't do this one at home. It's dangerous and expensive. One major place we find platinum used is in the jewelry industry. Like gold, platinum is extremely corrosion resistant and has a beautiful silvery luster, but without the chemical reactiveness of actual silver metal. Of course, it's much more expensive than silver by about 40 times. Any description of platinum jewelry would be incomplete without mention of the many crowns of England. Here we see the platinum crown of Elizabeth, the Queen Mother. This was made in 1937 and features the Koh-i-Noor diamond, one of the largest cut diamonds in the world, coming in at over 105 carats. Given its high value and non-corrosive qualities, you'd think platinum would make a good metal for coins. But it's a little too valuable for that. The 10th-ounce Liberty coin on the left is worth $100, even though you see it has a face value of $10, and the 1/25th-ounce coin with the fine cat from the Isle of Man is worth $50. These small coins would be too easy to lose. Similar to its use in jewelry, the tips of fountain pens can be plated with platinum and gold to keep them from corroding. Those nibs do spend the bulk of their lives soaking in ink. Of course, the platinum and gold also add to the physical and psychological value of the pen. An actual place where corrosion resistance was very important was in creating international standards. In 1889, the kilogram was defined as the mass of a cylinder made from an alloy of 90% platinum and 10% iridium stored in a vault in Paris. All other kilograms were compared to this standard. Originally, the cylinder was of pure platinum, but iridium was added to the original pure platinum kilogram standard to improve the hardness and increase the density while retaining the extreme chemical inertness. This was the world's standard for the kilogram until 2019. The kilogram is now based on fundamental physical constants reproducible in any lab, so finally the kilogram is no longer based on a physical artifact. Likewise, the meter was based on the distance between two marks on a platinum-iridium bar, similar to the one you see here. The meter is now based on the distance light travels in 299,792,458ths of a second And the second is based on 9,192,631,770 vibrations of a specific microwave given off by cesium-133 atoms. So again, no physical artifact is used for the meter anymore. Still, platinum was once involved. Believe it or not, we used to view photographs on paper rather than on screens. The vast majority of these prints were made with a process that involved light-sensitive silver. However, a similar process using platinum was used as well. Here we see two platinum prints, or platinotypes, of George Bernard Shaw on the left, and one of the marriage of King George VI and Queen Elizabeth, the Queen Mother. These prints have a very warm tone to them. Because of its resistance to chemical reaction, platinum makes an ideal material for labware when you're dealing with especially harsh chemicals. Here you see a platinum crucible, a piece of platinum mesh screen, and a perforated cone, which I have no idea what it was used for, but probably for filtering or straining if I were to hazard a guess. If you need to make measurements in corrosive liquids, platinum is your go-to electrode material. These are three different forms of platinum electrodes. As you heat most metals, the resistance to conducting electricity goes up. You can measure this resistance to figure out the temperature. Given platinum's chemical resistance and relatively high melting point, a resistance thermometer made with platinum wire makes a fine instrument. I just happen to have one right here. This is a platinum resistance thermometer, and in the end here is a coil of platinum. Let's get back to the slide there. I can show that to you closer up. The coil of platinum is seen there, and I think there's a little bit of oil in the tube as well, and that oil may be there to provide thermal conductivity from the glass to the platinum. Here's a graph of how the resistance changes when you change the temperature. At least in this temperature range, the change is beautifully linear. These are platinum electrodes, which can be applied to the body to either read weak electric signals or deliver electric stimulation. Some platinum compounds, such as cisplatin, carboplatin, and oxaliplatin, are used in chemotherapy for treating certain types of cancer. These compounds interfere with the DNA replication process in cancer cells. Aside from a microscopic bit, possibly absorbed from the environment, your body does not contain or use platinum, and it has no known biological functions. As usual, we'll end this talk with Mary Soonley's elemental haiku about platinum. In a basement vault, nestled within 3 bell jars, the measure of mass. In the next program in this series, I'll examine another precious and chemically resistant element, gold. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about the element platinum.